Welcome to our Engineers Newsletter live broadcast on Waterside heat recovery. I'm Jeannie Harshaw from Trane's Applications Engineering Department, and I'll be your host today. As we are all aware, energy and energy costs are getting a lot of attention these days. Natural gas prices last winter were almost double a year before. While they've dropped some this year, many of your customers are interested in finding ways to reduce heating energy cost. Waterside heat recovery can help with this. But before we dive too deep into today's broadcast, let's cover some of the housekeeping. Through our association with the American Institute of Architects, credit towards continuing education can be earned for viewing today's broadcast. If you're an AIA member, make sure you provide your member number to your local host before leaving today's session. In several states, this certification can also be applied to engineers' continuing education requirements. Please check your state's rules to see if this might be applicable. Today, we'll present information that should help the design engineer properly determine if heat recovery is justified. We'll discuss how heat recovery works and how it affects the chiller. Then we'll get into what's needed for implementation and system-level design and control strategies specific to heat recovery. Following the presentation, we'll answer some of your questions. Please fax them in at any time to the number on your screen. Now, many of you might be asking why a broadcast on Waterside heat recovery. Well, let's go back to the 70s, when in response to an energy crisis and an oil embargo, it became a decade where design engineers recovered heat from the chiller's condenser for use in other portions of the building or process. Now, at that time, Trane published a number of newsletters and manuals on heat and energy recovery. Then, during the building booms of the 1980s and 90s, interest in energy waned and heat recovery was used a lot less. As energy costs have again increased and there is a raised awareness of environmental issues, today we see renewed interest in recovered heat, such as that from the condensers of water-cooled chillers. One of the problems is that many of the people who design these systems are retired, so there's less familiarity with the application. To cover this information today, we have three presenters. First on board will be a familiar face, your previous host of the broadcast, Mick Schwedler, who will discuss reasons why and when heat recovery should be considered. Later, Mick will be joined by Court Nabuda, who will take us through heat recovery system control methods. Court will also cover specifics of centrifugal chiller operation. And another familiar face, Dave Guckelberger, will discuss code restrictions of potable water in heat recovery systems. Dave will join us again toward the end of the broadcast to walk through several system configurations and the benefits of each. We have a lot of information to cover, so let's get started. Mick, will you start with the reasons why to use heat recovery?
You bet. The first reason to use heat recovery is that it makes sense. In the same building, there are cooling and heating loads occurring simultaneously. Why not find a way to move the heat around in the building rather than rejecting the heat from the cooling process, then purchasing heat for the heating process? If the simultaneous heating and cooling loads are there, then heat recovery can be implemented for economic and environmental reasons or to satisfy local building codes. In many of these cases, it will be cheaper for the building owner to recover heat rather than paying to reject it. It gives a double economic benefit. Recovered heat reduces a heating load and cost and also reduces the ancillary power necessary to reject the heat, thereby reducing energy costs. Near the end of the broadcast, we'll touch on some important aspects to take into account when determining the return on investment of heat recovery. But beyond compelling economics, a major emphasis today is the positive environmental impact of energy recovery. More building owners are considering certification under the U.S. Green Building Council's Leadership in Energy and Environmental Design, or LEED, program. When energy is recovered, the site or building becomes more green or sustainable. Again, that double benefit. You don't have to expend energy to heat, nor do you need it to reject heat. Not only does heat recovery reduce resource use, but the reduction in purchased fuel reduces emissions to the environment. Reducing emissions may be beneficial for a variety of reasons beyond being an environmental steward. Burning fossil fuels such as fuel oil or natural gas increases site emissions. If the job site has already reached the maximum emissions level allowed by local code, recovering heat can satisfy future loads without consuming more fuel on site. This was the case cited by Ralph Cohen in his ASHRAE Journal article in August of 2003. By installing heat recovery chillers, their site was able to reduce purchased natural gas use by 83% compared with using fossil fuel boilers. Their reduction in nitrous oxygen emissions was over 5 tons annually, and due to the fact that they were not rejecting heat, they used 45 million fewer gallons of makeup water for their cooling towers. Even more importantly, the process taking place at the site was able to be expanded, rather than building an entirely new plant in a different location. This benefits the building owner both economically and from a public relations perspective. In addition, some locales are considering emissions trading. If such legislation or markets become common, trading the emissions credits is expected to be extremely valuable. A reason many people use waterside heat recovery is simply that standards in many building codes require it in specific applications, often through the implementation of ASHRAE Standard 90.1. Additionally, specific building owners may decide to mandate its use. For example, the U.S. Army Corps of Engineers publication, Humidity Control for Barracks and Dormitories in Humid Areas, states, the Army shall use condenser heat recovery in accordance with ASHRAE 90.1. Okay, let's look at those 90.1 requirements. ASHRAE ISNA 90.1 2004 requires heat recovery for surface water heating if the facility operates 24 hours a day, rejects more than 6 million BTUs per hour at design conditions, and has a design surface water heating load of over 1 million BTUs per hour. Once these limits are met, the required heat recovery is the smaller of 60% of the peak heat rejection load, or enough to preheat the peak service hot water draw to 85 degrees Fahrenheit. Such conditions may occur in healthcare facilities, dormitories, correctional facilities, hotels, or condominiums with central plants. Remember that this is a requirement of many local energy codes that adopt the International Energy Conservation Code. The requirement is included by either Chapter 7 or 8 of the 2003 version of the IECC. In addition to the surface water heating requirement, 90.1 does not allow simultaneous heating and cooling of supply air streams, whether it's done using reheat or by mixing of hot and cold air streams. There are exceptions that allow reheat to be used. For comfort cooling applications, the zone airflow must be reduced to the greatest of that required for ventilation by ASHRAE Standard 62, 0.4 CFM per square foot, 30% of design airflow, or 300 CFM. Many VAV systems will be able to reduce zone airflow to one of these limits prior to reheating the air and therefore comply with 90.1. However, a constant volume system would likely have to use the final exception. That is, recovering 75% of the reheat energy on site, such as from a chiller's condenser. When active humidity control is employed using a humidistat, there are different limits, but the general thought is the same. The amount of cooling being done has to be reduced prior to using new energy for reheat to one of the limits described by the exception shown here. Again, an exception to the dehumidification control requirement is allowed if at least 75% of the energy for reheating is site recovered. Recovered heat from a chiller's condenser is a method of satisfying that requirement. The locales shown in gold on this slide have already adopted ASHRAE 90.1 1999, 2001, or 2004 as a basis for their energy code, many through the International Energy Conservation Code. And remember, code only defines the minimum requirement. Even if you're in a locale that does not require energy recovery, it may still be beneficial for the building owner for economic or environmental reasons. Jeannie, your turn.
Thanks, Mick. To summarize, there are a number of reasons to use energy recovery. The first most people consider is ensuring they comply with the local energy codes. However, since code is the minimum requirement, some projects include energy recovery due to the return on investment. Finally, sometimes heat recovery is used to attain a specific level of LEED certification or to reduce emissions at the building site. Mick, take us through some of the common uses of waterside heat recovery.
Will do, but before we move on to discuss some of the uses of recovered heat, let's look at a question that is often asked. At how high a temperature should we recover heat? According to the 2004 ASHRAE Handbook of HVAC Systems and Equipment, for typical buildings, chillers normally provide water for space heating at 105 to 110 degrees F. Now this might seem counterintuitive if our first thought was to provide the hottest water possible. As we'll see in a few minutes, the water temperature has a significant impact on chiller efficiency. The ASHRAE Technical Committee responsible for the handbook gives this guidance based on balancing the possibility for hot water, the cost of that hot water, and the system design. Now, service water is defined as that hot water used for domestic or commercial purposes other than space heating and process requirements. ASHRAE 90.1 also gives some guidance concerning the temperature for service water heating, since it requires service water to be preheated to 85 degrees Fahrenheit. So for many service water heating applications, heat recovery temperatures of 85 to 95 degrees are used. And using ASHRAE's guidance for space heating, temperatures of 105 to 110 degrees Fahrenheit work well for space heating applications found in commercial or institutional facilities. Okay, there are many uses for recovered condenser water heat in a building. Let's look at a few of them. Within an industrial or commercial setting, there is often a need for process heat. Some possible uses are to make materials more malleable or to keep product at a specific condition while it cures. Quite often, these process loads require a constant or near constant temperature. Here's some general guidance on providing waterside heat recovery for these loads. First, look at the process load profile. Make sure there are simultaneous cooling loads, otherwise there will be no heat to recover in order to satisfy the heating process. As Dave will discuss, it may sometimes be advantageous to increase the cooling load on a chiller so the heat can be recovered. Next, select a chiller that rejects the amount of heat the process needs. While you may want to have a slightly larger amount of heat rejected, this approach will minimize the cost of the heat recovery system and allow more efficient operation. Finally, determine the process load temperature requirements and select a chiller accordingly. Putting in a safety factor here can have a dramatic effect on system cost and efficiency, as we'll see in a few minutes. Next, many commercial facilities use hot water for showers and laundry. That water leaves the facility and makeup water must be heated. Such facilities include hospitals, dormitories, and hotels. Dave will cover heating of potable water and code issues in a few minutes. Another use for heat recovery is hotels. Heating the pool with recovered heat may prove to be very cost-effective. A heat exchanger separating the condenser and pool water is needed due to the chemical composition of that pool water. And many times, recovered heat is used to increase the temperature of air. The most common uses are for increasing the temperature of supply air and preheating outdoor air. Let's look first at reheating the supply air stream in a constant volume system that has a constant leaving coil temperature. An example for this system is a high-tech manufacturing process with specific design humidity conditions. The amount of heat provided is dependent on the space temperature. This psychrometric chart depicts that even at design conditions, this space, with a fairly low sensible heat ratio, requires reheat. The amount of heating energy required is significant since the air has to be reheated prior to entering the room. This load can easily be satisfied using heat recovery. A second example is a constant volume system with active humidity control. During normal partial load situations, the coil supply air temperature is allowed to drift upward. However, if the space humidity rises too far, that supply air temperature is reset downward. With the colder air entering the space could subcool. So at some point, to keep the space from getting too cold, the reheat coil is brought online. This is another ideal reason for use of recovered heat. Finally, let's look at a variable air volume system. The coil supply air temperature is constant, and variable air volume is used to control the space temperature. In most applications, each VAV terminal has a minimum airflow setting. For example, it may be set to maintain the zone's ventilation requirement. If the space load drops far enough, this minimum position may cause the room to overcool. Heat recovery can be used to maintain proper space conditions. Many times these heating loads can be met with water temperatures of 105 degrees Fahrenheit, as supported by ASHRAE. Again, an ideal application for heat recovery from any chiller. Let's look at an example that will help us understand how the heat recovery temperature affects the system design. A variable air volume box is sized to deliver 2,000 CFM. The design supply air temperature is 55 and the design space temperature is 75. The minimum airflow setting is 30%, which corresponds to 600 CFM. If the cooling load drops to 0, this quantity of air must be heated 20 degrees Fahrenheit to avoid overcooling the space. This defines the maximum amount of reheat that needs to be provided. A one-row coil can satisfy this load if its entering water temperature is 113 degrees. As you can see, the water temperature difference across the coil is pretty low, and the fluid pressure drop is fairly significant. Remembering ASHRAE's guidance, couldn't we recover heat at a lower temperature? Since, as we'll see later, this 113 degree temperature adversely affects the chiller's energy use. Another option is to recover that heat at 105 degrees, but it requires a two-row heating coil. Due to that two-row coil, there is an increase in air pressure drop that must be considered during the analysis, since it raises the air system design static pressure and fan horsepower. However, at minimum airflow of 30%, the coil air pressure difference is greatly reduced, so the overall fan energy increase may be small. On the plus side, at 105 degrees, the coil fluid pressure drop is almost nothing compared to the single-row coil. This reduces pump energy. Balancing all these effects is important. Make sure that an analysis is performed so that the proper decision is made. More on that later. A final use of heat recovery is for preheating outdoor air. This was addressed by Cohen in his article. warming outdoor air generally requires a significant amount of heat. In many process applications, there is a constant cooling load. The heat that would otherwise be rejected to a cooling tower can be used to heat, or at least preheat, outdoor air by putting a heating coil into the outdoor air stream. Where only small amounts of outdoor air are being treated, the use of a small water-to-water heat pump may be beneficial. Just think of it as a little chiller. The evaporator portion of the heat pump can pre-cool return chilled water, and the condenser side can reject heat to a separate water loop used to preheat the outdoor air stream. A final reason to use energy recovery is to heat potable water. But there are some code issues that must be addressed. Dave, please take us through those issues.
Okay. Mick covered the reasons why heat recovery should be used and also some of the situations where it can be used. We saw that energy codes mandate the use of heat recovery in some applications. Now let's look at a case where the codes put some restrictions on how we use heat recovery. There are many commercial facilities, such as hospitals, dormitories, and hotels, that use water for washing, showering, and other everyday uses. All of these facilities require large quantities of potable water that must be heated. A heat recovery condenser may be able to meet these loads, or at least offset some of the heating requirement. But be aware that heating potable water may require a higher level of isolation between the chiller and the water than other forms of heat recovery. The International Plumbing Code requires that all heat exchangers used in potable water systems be designed to prevent the transfer of toxic materials to the water system. It's important to note that the definition of the word toxic, as used by the International Plumbing Code, is different than the definition provided by ASHRAE. The definition used for the international codes is found in the International Fire Code. I've included the wording from the Fire Code on a handout that should be available at your viewing location. Bottom line, be sure to talk to your local code inspector to see what is required in your area when applying heat recovery to potable water systems. Where isolation is required, it is typically done with a vented double wall construction, either at the chiller or in a separate heat exchanger. A leak in either the water loop or the refrigerant loop will result in the leaked material being vented out of the openings in the double-walled tubing. Now let's turn our attention to the heat recovery chillers themselves. We'll start with an overview of the various chiller configurations that are used. This figure shows a generic single condenser chiller used to satisfy cooling loads. The heat is transferred from the cooling load to the evaporator of the chiller, to its condenser, and finally to the cooling tower that rejects the heat to the ambient air. In some cases, this standard chiller configuration can be used for heat recovery. The chiller's primary mission is to provide chilled water at the design set point. The chiller controls modulate compressor capacity based on the temperature of the water leaving the evaporator. The amount of heat produced by the chiller is determined by the cooling load and may be more or less than the heating loads require. The chiller can only be operated in this configuration when the need for heat exceeds the heat output of the chiller. If more heat is produced than the loads will absorb, the condenser temperature of the chiller will rise and the chiller will experience operating problems or shut down. By adding a heat exchanger to the condenser water loop, the excess heat produced by the chiller can be rejected to the cooling tower. The chiller is set to maintain a fixed leaving chilled water temperature. The heat generated is used by the heating loads, and when more heat is generated than needed, the excess goes to the cooling tower. If the chiller will be fully loaded when there is no heating requirement, the heat exchanger must be sized for the total heat rejection of the chiller. A variation of this configuration uses a closed-circuit cooling tower and a three-way valve instead of the heat exchanger. But be aware that both of these configurations are less efficient than other methods of condenser water heat recovery because the intermediate heat transfer step and the additional pump energy. By changing how the chiller is controlled, the standard chiller configuration can be used to provide modulated heat output. We call this a heat pump chiller because heating is the primary mission of the chiller. The compressor capacity is modulated based on the hot water temperature entering or leaving the condenser. Heat is the desired output, and the cooling effect is secondary. Cooling is not done to a set point. The chiller simply does the amount of cooling required to provide the desired amount of heat. Of course, a sufficient cooling load must exist to provide that heat. Most standard water-cooled chillers can provide suitable condenser water temperatures for heat recovery. As mentioned by Mick, a condensing water temperature of 105 degrees is often all that's needed, and this is just a slightly elevated refrigerant condensing temperature. Another way to separate the heating and cooling demands is to use a chiller with a heat recovery condenser. This option, typically available on centrifugal chillers, provides two separate condensers. One condenser is piped to the heating loads and the other to the cooling tower. When the heating loads exceed the cooling loads, all the heat is rejected through the heat recovery condenser. If the amount of heat generated exceeds the heating loads, the excess heat is rejected via the standard condenser. Either of the condensers can reject the full amount of heat generated by the cooling loads. The final chiller configuration I'll cover is the second type of dual condenser chiller. In this case, the heat recovery condenser, called an auxiliary condenser, is much smaller than the standard condenser and is not meant to reject the entire condenser load. Chiller capacity is modulated to meet a cooling set point, and the standard condenser is connected to a cooling tower. Heat rejection to the auxiliary loop is unregulated and will occur only if the water feeding into the auxiliary condenser is at least as cold as the cooling tower water. As shown on the slide, this configuration is commonly used to preheat makeup water for a boiler. The auxiliary condenser option does not recover a large amount of heat, but it is easy to control and can provide a slight efficiency boost to the chiller. In the next section of the broadcast, Court will explain the two condenser chiller options in greater detail.
As Dave already mentioned, there are two primary types of heat recovery condensers for centrifugal chillers. These are classified by the size of the heat recovery condenser and the control scheme that is in place. The first dual condenser option is what most people think of when heat recovery comes to mind. In this configuration, the heat recovery condenser is the same physical size as a standard cooling condenser. This enables the secondary condenser to reject all the chiller heat to the hot water loop. This type of heat recovery condenser is actually called a heat recovery condenser. Now this is where it gets a little confusing to some people. Any type of condenser that is used to preclaim heat is generally referred to as a heat recovery condenser. But to most chiller manufacturers, such as Trane, the term heat recovery condenser only applies to a secondary condenser of equal size. The amount of heat rejected through a heat recovery condenser is controlled by the temperature leaving the standard condenser. As the water temperature leaving the standard condenser is reduced, the condensing pressure drops and the heat recovery leaving water temperature decreases as well. Conversely, increasing the leaving water temperature causes the condensing pressure to rise. This rise in pressure results in a higher leaving heat recovery temperature. Or said another way, by varying the standard condenser's water temperature, you're essentially directing where the condenser refrigerant will reject its heat. Heat recovery chillers sacrifice cooling efficiency for higher hot water temperatures. Heat recovery condensers are generally used when temperatures in the hot water loop exceed 95 degrees Fahrenheit. The chiller configuration can also operate as a cooling-only chiller if dedicated heating is no longer required. The second dual condenser option consists of a secondary shell that is smaller than the standard condenser. This is often called an auxiliary condenser. Because of its smaller size, an auxiliary condenser cannot reject all the chiller heat to the secondary water loop. This means that the cooling tower loop is always in operation. The auxiliary condenser does not require additional controls, and you essentially get what you get based on the refrigerant temperature. This also means that the leaving water temperature for an auxiliary condenser is always lower than the standard cooling condenser. These colder temperatures in the auxiliary condenser increase the chiller efficiency when it is in operation. Due to these lower temperatures, an auxiliary condenser is commonly used to preheat incoming groundwater for service or potable water. This results in auxiliary condenser leaving water temperatures ranging from 70 to 85 degrees Fahrenheit. This chiller configuration can also operate as a cooling-only chiller by restricting the water flow through the auxiliary condenser. The following slide shows a brief summary of the two condenser options that were just discussed. Again, the heat recovery condenser is the same physical size as the standard cooling condenser. It is intended for large heating loads at higher temperatures. The heat capacity is controlled by regulating the cooling condenser temperature. Chiller efficiency is also decreased. The auxiliary condenser is smaller than the standard cooling condenser and is utilized for smaller or non-constant heating loads. Its heat capacity is not controlled and it produces temperatures lower than the standard cooling condenser. Chiller efficiency is increased due to its lower operating temperatures. Mick, will you now cover the basics of lift and positive displacement compressors?
You bet, Court. When applying heat recovery, it's important to understand that different compressor types respond in different ways to condensing conditions. Positive displacement compressors, scroll, helical rotary, and reciprocating, react to condenser pressure differently than do centrifugal compressors. Regardless of the compression method, the condensing pressure, and therefore temperature, must be kept below the allowable limits for the chiller. This limit information can be obtained from the manufacturer. So let's look at a few basics, then compare how having a chiller operating in a heat recovery mode changes the performance of that chiller. The amount of work a compressor must perform is proportional to the pressure differential between the evaporator and the condenser. This is often referred to as the lift. At elevated temperatures used for heat recovery, the condenser pressure is higher, so at the same evaporator temperature, the lift is increased. Depending on the compressor type, positive displacement or centrifugal, the compressor reacts differently to this change in lift. Let's look at that. The theoretical vapor compression refrigeration cycle for a helical rotary or screw water chiller can be plotted on a pressure enthalpy chart. The refrigerant leaves the evaporator as saturated vapor at point 1 and flows to the suction end of the compressor. The refrigerant flows across and cools the motor, then enters the compression chamber. The refrigerant vapor is compressed in the compressor to a high pressure and temperature at point 2. Energy input to the motor and compressor is imparted to the refrigerant as superheat. Superheated refrigerant vapor leaves the compressor and enters the condenser. Water flowing through the condenser absorbs heat from the hot, high-pressure refrigerant. This reduction in the heat content of the refrigerant vapor causes it to de-superheat to point 3, condense into liquid, point 4, and further subcool, point 5, before leaving the condenser to travel to the expansion device. The pressure drop created by the expansion process causes a portion of the liquid refrigerant to evaporate. The evaporating refrigerant absorbs heat from the remaining liquid refrigerant. The resulting mixture of the cold, liquid, and vapor refrigerant enters the liquid vapor separator at point 6. Here the vapor is separated from the mixture and routed directly to the suction side of the compressor, that's point 1, and the remaining liquid enters the evaporator, point 7. When heat recovery is performed at an elevated temperature, the condenser pressure and temperature rise. This requires the compressor to perform more work. The amount of work the compressor must perform is proportional to the difference between the evaporator and condenser pressures. We can see that at the elevated heat recovery temperature that the lift and therefore the work has increased. So, how does this increase in lift affect chiller performance? This graphic shows how the temperature leaving the condenser affects the chiller's capacity. Note that this graphic assumes that the chiller and its shells are designed for the temperature shown. Always contact the chiller manufacturer for information on the chiller being considered. Thinking back to our VAV box example, let's look at how the chiller capacity would be affected. If we selected a one-row heating coil, the leaving condenser water temperature had to be 113 degrees, and chiller capacity is reduced by about 12%. If instead we select a two-row coil, we can reduce the water temperature to 105, and the capacity is only reduced about 7%. When the cooling capacity is reduced, the chiller may no longer be able to satisfy the cooling load, so that needs to be checked. In addition to this capacity reduction, the power necessary to provide the compressor lift increases. Although the chiller can operate in a heat recovery mode, we need to analyze whether the additional power required and the reduction in capacity warrant the benefit. Again, the next figure is intended to be used only for comparative purposes. Always contact the chiller manufacturer for information on the specific chiller being considered. The slide generically shows how two positive displacement compressor technologies react to elevated condensing temperatures and pressures. Because both power and capacity are changing, the power draw is shown in units of kW per ton. Going back to our VAV example, at 113 degrees, leaving condenser water temperature, the kW per ton of a small screw chiller has increased over 35%. If we instead supply 105 degree water, the kW per ton rises only 16%. On the other hand, if we try to supply very hot water temperatures, kW per ton gets 80% worse. That's almost double. The bottom line is that as the heat recovery temperature goes up, capacity goes down, and so does efficiency. This is one of the reasons the ASHRAE handbook stated that most buildings use 105 to 110 degree water for space heating requirements. Now that we've covered positive displacement chillers, let's have Court take us through how centrifugal chillers react to this change in lift.
The pressure enthalpy chart for a two-stage centrifugal chiller is similar to a positive displacement machine, except for a few additional points created by the flash economizer. Heat of compression is reduced from points 2 to 3 due to the refrigerant gas introduced by the flash economizer, while points 7 and 8 show the liquid vapor separation in the economizer caused by the first expansion device. One other difference is a lack of subcooling at point 6 due to the cycle process. Just like positive displacement compressors, power consumption is increased due to the higher pressures associated with heat recovery. However, the differences in the pressure enthalpy chart between a positive displacement compressor and a centrifugal compressor are not important when heat recovery is concerned, but the physical differences in the compressors themselves are. The first key point to keep in mind is that there is no physical component that forces refrigerant through a centrifugal compressor. The refrigerant flowing through the compressor is its own driver and its own inhibitor to prevent refrigerant from flowing in the wrong direction. This mode of operation makes centrifugal compressors very efficient at their design point, but how they react to differences in lift and refrigerant flow are quite different. The possibility of surge is another factor that has to be considered. A centrifugal compressor uses the principle of dynamic compression, which involves converting one form of energy to another. In this case, the conversion of kinetic energy to static energy increases the pressure and temperature of the refrigerant as it moves through the compressor. This process is achieved through the use of a rotating impeller. First, the center, or eye of the impeller, draws refrigerant vapor into its internal radial passages. The rotation of the impeller accelerates the refrigerant as it travels through the passages, increasing the velocity and kinetic energy of the refrigerant. After leaving the impeller, the refrigerant vapor continues through a stationary diffuser passage where it eventually widens out into the volute. The larger cross-sectional area of the volute causes the refrigerant to slow down in order to maintain the same flow rate. As the velocity decreases in the volute, the kinetic energy is converted to static pressure. The principle of dynamic compression is difficult for some people to understand. Why would refrigerant pressure simply increase due to velocity changing? Dynamic compression is similar to the static regain method used in duct design, where velocity pressure is converted to static pressure. Let's look at the velocity-pressure relationship that acts on the refrigerant vapor. You can see that these forces can be broken down into two primary components. One is the radial vector, V sub r, which is proportional to the refrigerant flow rate through the compressor. The other is the tangential vector, V sub t, which is proportional to the rotational speed and the diameter of the impeller. Together these form the velocity vector r, which is proportional to the kinetic energy of the refrigerant. Therefore, the ability of a compressor to produce static pressure can be changed by the refrigerant flow rate, rotational speed, and diameter of the impeller. For heat recovery, the compressor must produce a larger pressure differential between the evaporator and condenser as compared to a standard cooling application. Since the refrigerant flow rate is indicated by the chiller's cooling capacity, the higher pressure requires a larger diameter impeller, or a higher rotational speed if the compressor is gear driven. The relationship between temperature and power consumption for a centrifugal compressor can be seen here. Starting with 85 degree entering heat recovery temperature, a chiller with the same heat exchanger shells and compressor can maintain the same cooling capacity up to a 100 degree entering heat recovery temperature at the same 20 degree delta T. This assumes the impeller diameter was allowed to increase with the higher temperatures. The additional power required to perform heat recovery is shown in relation to that same identical chiller operating at ARI conditions. One thing to also consider is that a chiller becomes more inefficient in cooling mode as the heat recovery impeller diameter is increased. So as heat recovery temperatures rise, the chiller efficiency decreases in both heat recovery and cooling mode. When performing an energy analysis, be sure to take into account the chiller's efficiency reduction and the amount of heat recovered. As already mentioned, standard cooling efficiency is reduced with the larger impeller diameters required for heat recovery. For this reason, variable speed drives are sometimes considered for heat recovery chillers. If a chiller spends most of its time in heat recovery mode, higher lift requirements limit these savings because the drive can't slow down. It is also important to know that incoming water temperature for the standard cooling condenser has no impact on chiller efficiency when in heat recovery mode. Even if you can lower the cooling tower set point, the heat recovery condenser still requires the same amount of lift to reject the same amount of heat. Also remember that a variable speed drive saves energy by riding the surge line of a centrifugal compressor. Since heat recovery is more prone to compressor surge, adding another variable into this equation is not always recommended. We'll cover the details of surge in a few minutes. The slide shows a quick example of what was presented on the previous graph. Here, two chiller selections are shown. One selected for cooling only and another selected for heat recovery with 105 degree leaving water. The same compressor and shells were used on both of these selections, only in the impeller size was allowed to change. In this case, a cooling only chiller was selected with a COP of 6.2. The same chiller with the larger impeller and heat recovery condenser is now at a 5.6 COP when in cooling mode. The even lower COP value in heat recovery mode is expected due to the higher lift requirements. Due to the larger impeller size, the efficiency of the heat recovery chiller in cooling mode is reduced compared to the cooling only chiller. When using centrifugal chiller in a high lift application, it is extremely important to understand compressor dynamics at part load. Larger pressure differentials challenge the ability of a compressor to unload due to a condition called surge. Consider a constant speed compressor impeller and the velocity vector that were discussed earlier. As the load on the chiller decreases, the inlet vanes restrict the refrigerant flow into the compressor. This decrease in the refrigerant flow reduces the radial vector V sub r. In this case, the tangential vector V sub t decreases as well. Now, why would V sub T decrease with a constant impeller speed? We know that the impeller can't magically change diameter inside the compressor. V sub T becomes smaller due to the pre-swirling of the refrigerant caused by the inlet vanes. Since the refrigerant is already rotating as it enters the compressor, the effective rotational speed seen by the refrigerant is reduced. If variable speed drives are brought back into the picture, V sub T could also be reduced due to the slower compressor speeds. When both vectors are reduced at part load, the resultant velocity vector R, which is proportional to the kinetic energy, is also reduced. As the load is further reduced, the velocity vector can eventually reach a point where the kinetic energy of the refrigerant is no longer large enough to overcome the static pressure in the condenser. When this occurs, the refrigerant vapor flows backwards through the diffuser passages and into the impeller. This instantaneously reduces the pressure inside the impeller passages, allowing the compressor to reestablish the proper direction of refrigerant flow, only to repeat the process again. This unstable condition is known as surge. The refrigerant continues to flow backwards and forwards through the compressor, generating noise and vibration. Prolonged surge is not good for the compressor and should be avoided. To avoid surge on an existing chiller, you can either increase the refrigerant flow or reduce the lift. Sometimes surge on a heat recovery machine is prevented by maintaining a large cooling capacity and high heat rejection through the heat recovery condenser. Sometimes chilled water reset is performed. If your heat recovery chiller is operating during cooler months, dehumidification might not be as high of a concern. But the primary issue that needs consideration is whether you regulate your heat recovery capacity on the entering water temperature or the leaving water temperature. For centrifugal chillers, you need to target the entering heat recovery temperature. The curves on the graph represent the performance of a typical two-stage compressor over a range of inlet vane positions. The dashed line that runs across the top and to the far left of the vane curve is the surge boundary. The important items to remember on the graph are point A, which is your design heat recovery operating point, and the unloading lines AC and AB. Now let's look at the graph with all the extra clutter removed. Here's the same graph, but now we're only looking at the two unloading lines and the surge boundary. By looking at this graph, it becomes clear why you maintain a constant entering heat recovery temperature. Maintaining the leaving heat recovery temperature doesn't give the centrifugal compressor any lift reduction, and then the unloading line, AC, shows how quickly you can run into problems by controlling the chiller this way. The line AB shows unloading by maintaining a constant entering heat recovery temperature. With this control strategy, the leaving heat recovery temperature is allowed to float up and down in response to the chiller's cooling load or required heating capacity. By allowing the leaving heat recovery temperature to float, you give the chiller some lift reduction and allow it to unload more successfully. Now this seems counterintuitive for a heat recovery chiller's application. For example, if you specify a certain leaving hot water temperature of 110 degrees, you want 110 degrees. But remember, as the name implies, that this is a heat recovery chiller. Its primary function is to provide sufficient cooling capacity at a specified leaving water temperature. The heating that you get from the chiller is an additional bonus. Remember that this is still a high lift chiller. Depending upon your desired heat recovery temperatures, good unloading for a heat recovery chiller may be 50% part load, or even as high as 75% part load. The minimum unloading point depends upon the design conditions and the centrifugal chiller selection. Let's look at a quick example showing a heat recovery chiller's unloading capabilities. This slide shows a 400-ton heat recovery selection with a 95 to 115 degree temperature spread in the heat recovery condenser. The first column shows the initial selection at 400 tons with all the heat rejection going to the heat recovery condenser. The chiller is operating at a 0.868 kW per ton with a heat rejection of 5,900 MBH. The second column shows the same chiller at its minimum unloading point while maintaining a constant entering heat recovery temperature. With a minimum cooling capacity of 310 tons, this chiller is able to unload to 78% of full load tons while still maintaining full heat rejection. The leaving heat recovery temperature dropped from 115 degrees to 111 degrees while providing a heating output of 4,600 MBH. The third column shows the chiller's minimum unloading point while maintaining a constant leaving heat recovery temperature. Through this example, it becomes very clear why this control strategy is not recommended. By maintaining the leaving heat recovery temperature, this chiller was capable of unloading to 380 tons before encountering surge. At 95% of the full load cooling tons, this severely limits the chiller's operating envelope. Now this was just one example of a chiller unloading in heat recovery mode. Depending upon machine variables such as shell size, heat exchanger surface, compressor size, and impeller size, sometimes the minimum unloading point can be improved. When specifying a heat recovery chiller for your application, make sure the chiller manufacturer provides you with the unloading capabilities for your heat recovery chiller. This information is critical to determine if a heat recovery condenser is viable for your application and the required system configuration is met to make sure it operates correctly. Next, Mick will discuss Waterside heat recovery control strategies for single condenser chillers.
Great stuff, Court. Regardless of the compression method, when a chiller is applied in heat recovery, condenser water temperature control is required in order to remain within the operating limits of the chiller. We'll cover some system and control options that are available. All examples here assume that the cooling tower water is kept separated from the heating loop. Scroll, helical rotary or screw, and centrifugal chillers may all have single condensers. We'll look at methods used to maintain a constant entering condenser water temperature. This slide shows a single bundle condenser using a heat exchanger to separate the tower water from the heating loop. The task of the control system is to maintain the condenser entering water temperature. First, let's look at the upper right corner of the diagram. To provide heat to the load, a valve, V1, is controlled by the water temperature coming from the heating loads, T1. An auxiliary heat source may be required if the condenser leaving water temperature is not high enough. Next, we'll consider the control to operate the chiller in a heat recovery mode. During cold outdoor temperatures that would lower the condenser water temperature too far to allow heat recovery, the diverting valve in the cooling tower loop, V2, modulates to maintain the condenser entering water temperature, T2. Once the valve is wide open, the T2 signal is used to control the cooling tower fan to maintain the desired condenser entering water temperature. The difference between this configuration and a normal cooling configuration is that the heat rejection side is maintaining the temperature on the chiller side of the heat exchanger. Let's look at how this operates at various times of the year. When there's no heating load, there's no flow to the heating load. All heat must be rejected through the heat exchanger and then the cooling tower. Our next operating mode has a heating load, and the heat recovered from the chiller can satisfy the entire heating load. Since there's a heating load, hot water is allowed to flow to that load. The tower and V2 operate to maintain temperature T2. Finally, at some point, the heat rejected from the chiller's condenser can no longer satisfy the heating load. At this point, the water flow through the cooling tower is shut off, and auxiliary heat is added as necessary. This strategy should be used for heat recovery systems that are using entering condenser water temperature as the control signal. This is almost always used for centrifugal chiller applications in order to avoid surge, and can also be used for positive displacement chillers. However, there are some applications in which a constant leaving condenser water temperature is desired. In such a case, the control for centrifugal chillers is different than for positive displacement chillers. Let's look at the centrifugal chiller heat recovery system control first. Recall that Court discussed the issue of surge with centrifugal chillers. If a constant leaving condenser water temperature is desired, this fixes the condensing pressure. So unloading would be between points A and C. If the load drops and the lift remains constant, the chiller can surge. If instead the chiller was controlled using constant entering condenser water temperature, the chiller would unload between points A and B. Another method to avoid entering surge as the cooling load drops is allowing the evaporator pressure to rise. This is done by allowing the chilled water temperature to rise. In this case, the chilled water temperature was allowed to increase by 6 degrees. Now, while this keeps the chiller from surging, the chilled water temperature may no longer meet the system requirements. So how does this look on our control diagram? In response to condenser leaving water temperature, T4, the leaving chilled water set point, T3, is reset upward to unload the chiller and decrease T4, and downward to load the chiller and increase T4. On Trane centrifugal chillers, the unit control panel has an automated function called hot water control. It's a mode which allows the chiller to operate in this manner. Now, some people refer to this as a heat pump or heating mode. No matter what it's called, using this control method, the primary function of the chiller is to satisfy the heating load. A secondary byproduct is the chilled water that is produced. Because the chilled water temperature, T3, varies when this application is required, the chiller is most often piped in a side stream position. Dave will discuss the system configuration a little bit later. On a positive displacement chiller, leaving condenser water temperature control is much simpler. Just move the T2 sensor to the leaving side of the condenser. Remember from our earlier discussion that as long as the chiller is within its operating limits, this can work fine. But both chilled water capacity and chiller efficiency will be reduced. Make sure that these are both accounted for in the analysis. Court, how about taking us through condenser water control when we have two condensers on a centrifugal chiller?
Now let's discuss heat recovery temperature control for a dual bundle centrifugal chiller. For the following examples, we're going to use a constant flow tower with a bypass valve, and on the heating loop we have a pump supplying the heating condenser. There are several variations on how this system could be implemented, which is discussed in the Waterside Heat Recovery Applications Manual. Remember that we are maintaining the entering heat recovery temperature on these slides, which is labeled T2. On this slide, no heating load is present. Since there is no water flow through the heat recovery condenser, the chiller operates in a normal cooling mode, rejecting all of its heat out to the cooling tower. Next, we have a modulating heating load. Only a partial amount of the heating capacity is needed from the heat recovery condenser, so T2 needs to be maintained. In this situation, the bypass valve, V2, and the cooling tower fans modulate to control the water temperature in the standard condenser. As T2 rises, more flow is diverted to the cooling tower. This rejects more heat to the cooling tower, and T2 drops to its control point. If T2 drops, less water is sent out to the cooling tower. More heat is rejected to the heat recovery condenser, and T2 rises back to its control point. On this slide, all the available heat from the chiller is being rejected through the heat recovery condenser, and an auxiliary heat source is needed to satisfy the entire heating load. If properly controlled, the leaving temperature from the auxiliary heating system, T1, is modulated to maintain a constant entering temperature to the heat recovery condenser, T2. In this situation, the standard cooling condenser is inactive. Again, please refer to the applications manual for configurations and control strategies. Now Dave will discuss popular configurations for Waterside heat recovery systems.
Now that we know how a heat recovery chiller works and how it can be used, let's turn our attention to look at where the heat recovery chiller fits into the chilled water system. System placement is important because the amount of heat recovered from a chiller is limited by chiller load. How the chillers are loaded depends on the chilled water system configuration. This section discusses the advantages of various system configurations, specifically with respect to heat recovery. For more information about the systems discussed here, please refer to the Trane Applications Manual, Multiple Chiller System Design and Control. Each of the configurations I'll review has its advantages and disadvantages. The system that's right for your building depends on your specific conditions, but for the sake of comparison, I'll use the conditions shown on this slide. Design chilled water temperatures are 56 degree entering and 40 degree leaving. There are two 500-ton cooling-only centrifugal chillers with a design chilled water flow rate of 750 GPM and one 200-ton heat recovery screw chiller with a design chilled water flow rate of 300 GPM. The present heating load is 2,000 MBH and the building cooling load is 550 tons. Return water temperature from the cooling load is 56 degrees. Even though we are holding the building load conditions constant in our example, the amount of heat that can be recovered changes with system configuration. Recovered heat is directly proportional to the load on the evaporator of the heat recovery chiller. For simplicity, we'll ignore the motor heat and use the evaporator temperature differential to indicate load. The amount of heat available from the evaporator water is determined by a simple heat transfer equation. Heat out equals mass flow times the specific heat times the temperature difference. For our conditions, this can be reduced to heat out equals 150 times the delta T. Let's start our system review by looking at the popular primary-secondary arrangement with all the chillers on the same side of the bypass line. In this arrangement, all of the operating chillers see the same return water temperature. To meet the cooling load, the heat recovery chiller and one of the cooling-only chillers are operating. At this operating point, surplus chilled water flows through the bypass line and drops the return temperature to these chillers to 52.6 degrees. Using our heat transfer equation, we calculate that 1,890 MBH of heat is available. Our required heat load is 2,000 MBH, so we're 110 MBH short. On the plus side, the cooling loads are always provided with chilled water at the design system temperature, and the water flow through the chillers and loads is typical for this system. We can preferentially load the heat recovery chiller by moving it to the load side of the bypass line. In this location, it always receives the warmest return water temperature. Using our heat transfer equation, we see that 2,400 MBH of heat will be produced. But we only need 2,000 MBH, so 400 MBH will have to be rejected to the cooling tower. As with the previous configuration, the cooling loads are always provided with chilled water at design, and the water flow through the chiller and the loads is as we would expect. It's possible to reset the leaving chilled water temperature of the heat recovery chiller so that the cooling load matches the heating load. But this increases the temperature of the chilled water being supplied to the cooling loads. Because this causes the cooling loads to use more water, both the system supplied temperature and the flows will be upset. An alternative method for preferentially loading the chiller is to place it in the side stream position. In this position, the chiller has access to the warmest return water temperature and, in our example, can produce 2,400 MBH of heat. An advantage of the side stream location is that we can use chilled water reset to control the heat output of the chiller without disrupting the supply water temperature to the cooling loads. And the warmer leaving chilled water temperature allows the compressor to operate more efficiently. This configuration also eliminates the need to connect the chiller to the cooling tower, which simplifies both the chiller and the chilled water piping. For our example, the reset results in a chilled water set point of 42.7 degrees for the heat recovery chiller. The slide shows the resulting system water temperatures. Note that by placing it in the side stream arrangement, the heat recovery chiller changes the chiller plant flow dynamics. Because the side stream chiller lowers the return water temperature, it may create a situation where multiple cooling-only chillers are running when only one is needed to meet the cooling load. The cooling-only chillers must be selected for the design delta T, even though they will experience a reduced delta T whenever the heat recovery chiller is running. One way to correct the imbalance in flow is to increase the flow rate through the operating cooling-only chillers. A control sequence must be set to increase the chiller flow as the return water temperature to the chillers increases. Of course, the chiller pumps must be selected for the increased flow, and the flow can't exceed the maximum allowed for the chiller. This slide shows a summary of the load conditions for our example. Picking different system requirements or even a different load point for this example will change the outcome, but there are a few important points that we can take away. As with real estate, location matters. The optimal location depends on your requirements. The negative auxiliary heat shown for the preferential location is not necessarily a disadvantage because this heat must be rejected whether it's from the cooling-only chiller or from the heat recovery chiller. Where you place the chiller can also give you some flexibility in how it's controlled. In a side stream location, the chiller can be controlled as though it's a heat pump. Compressor capacity is adjusted to meet the heating load, not the cooling load. When operated as a heat pump, cooling is a byproduct. Heat recovery chillers, controlled as heat pumps, placed in a side stream arrangement, don't have to be located in the chiller plant. If there are tempering requirements necessary at a few remote air handlers, recovering heat at the central plant and piping it to the air handlers may be too costly. In this situation, it makes more sense to put a small heat recovery chiller at the remote location. The chiller is sized for the heating requirements, and small heating and cooling pumps are installed in the fan room. This variation of the side stream configuration is referred to as distributed side stream. Now let's turn our attention to the heat recovery chillers in variable primary flow systems and see what happens for our example conditions. The slide shows the heat recovery chiller in parallel with the two cooling-only chillers. In the standard design, chiller valves open when the chiller is turned on and close when the chiller is turned off. When the heat recovery chiller is the only chiller operating, it is able to do full heat recovery. When more than one chiller is operating, they share the load proportionally. Some designers replace the on-off chiller valves with modulating valves and attempt to manipulate the flow through the chillers to preferentially load the heat recovery chiller. In our experience, this is extremely difficult to accomplish, and these systems are unlikely to work well. Another configuration of the variable primary flow system includes one pump per chiller. Dedicated pumps make it simpler to operate a variable primary flow system with different sized chillers. However, they don't make it any easier to preferentially load the heat recovery chiller. All pumps will operate to produce the same pressure, so they will run at close to the same speed, and flow rates will be proportional to design. Again, one may attempt to use modulating valves to achieve preferential loading, but this is not a simple control sequence. Placing the heat recovery chiller in a side stream arrangement makes it easier to preferentially load. It can be controlled to meet its design cooling set point, in which case it may reject more heat than can be used, or it can be controlled as a heat pump, providing only the required amount of heat. If the chiller has a heat pump control mode, capacity is modulated based on the leaving condenser water temperature. When a heat pump control mode isn't available, capacity modulation is typically accomplished by resetting the chill water set point based on the heat load requirements. It's also possible to adjust the chiller capacity by varying the chilled water flow through the chiller barrel. When varying the water flow, heat recovery capacity control is accomplished by changing pump speed rather than adjusting chilled water set point. While this is theoretically possible, maintaining constant flow and changing the chilled water set point is less complicated and more efficient. In summary, when using a heat recovery chiller in a variable primary flow system, the side stream arrangement is preferred. Before closing this section, I'd like to address one more system alternative that may be useful. Recall that for a system to benefit from heat recovery, there must be simultaneous heating and cooling loads. In many buildings, especially those with economizers, as the cooling load decreases, the heating load increases. As a result, there may be heating loads that are unmet due to insufficient cooling load. These can be met by providing a separate heat source or by providing some false load to the chiller. One method of providing a cooling load for the heat recovery chiller is to false load it by mounting a coil in the exhaust air stream. Since the temperature of this air will be close to the space air temperature, it provides a cooling load. When the rest of the building's cooling load falls below what is needed to provide heat, water may be passed through this coil and heated, providing a load to the chiller. We encountered one building that required an all-electric HVAC system. Compared to electric resistance heat at a COP of 1, the heat recovery chiller with a COP of 3 was a clear winner, even though the chiller produced excess cooling that had to be dissipated by the exhaust airstream. When we think of chillers as heaters and start working through the system logic, there are times when heating is more important than cooling, and chilled water becomes what our system is rejecting. Although this is counterintuitive, the important thing to remember is that such a system may be the most efficient to own and operate. Coming up next is the final section of our broadcast, where Mick will cover the analysis tools available to model the economics of heat recovery systems. Mick?
Whether a heat recovery meets our customer's economic criteria is dependent on heating and cooling loads occurring simultaneously and for enough hours to warrant heat recovery. Accurate analysis of heat recovery systems is critical. Accounting for simultaneous heating and cooling loads is imperative. Often there's a temptation to use methods such as equivalent full load hours or bin analysis. Simplifying assumptions inherent in these methods leads to inaccuracy, especially when applied to heat recovery systems. For example, the equivalent full load hours method ignores part load operation of chillers and does not account for simultaneous heating and cooling loads. Bin analyses usually relate load and chiller operation to outdoor conditions. With internal and solar loads being a significant portion of building load, the bin analysis methods are rarely sufficient. So avoid using either equivalent full load hours or bin methods to analyze heat recovery systems. Now, there are some important program capabilities to consider when using any analysis tool to examine heat recovery systems. Coincident cooling and heating loads must be calculated. Also, make sure the program can account for various fuels. For example, so that systems with electric chillers and natural gas boilers can be modeled. Often, utility rates include time of day usage and demand charges. Make sure the actual utility rates can be modeled. Remember that when chillers operate in heat recovery, that their capacity and efficiency change significantly. Make sure the program can analyze this. Look for a program that can accurately model system configurations, such as the side stream configuration Dave discussed, that may be used in heat recovery applications. And if emissions reduction is important, the analysis tool should be able to show reductions in substances such as carbon dioxide, nitrogen, oxygen compounds, and sulfur dioxide when comparing the heat recovery alternative with other alternatives. To make sure the analysis is accurate, be sure to input the different efficiencies at the cooling only temperature and heat recovery temperature so that the analysis is valid. Shown here is a screen from Trace Chiller Plant Analyzer with an example input for a small helical rotary chiller recovering heat at 105 degrees. At cooling only conditions, this is a 70-ton chiller operating at a kW per ton of 0.925. At the heat recovery conditions, the chiller can only make 66 tons, and its kW per ton has risen to 1.076. Now, some tools that fulfill all these requirements include System Analyzer, which can be used for high-level scoping analyses. Comparisons can be made in a short amount of time, usually less than an hour. Another tool is Trace Chiller Plant Analyzer. This program reduces the input time for the building, but allows full analysis of the chilled water plant and economic rates. Again, analysis can be done in less than an hour. Finally, Energy Plus, Trace, and HAP can be used. These are full energy simulation tools that use detailed hour-by-hour calculations to calculate energy consumption, power demand, and related costs. These tools may be used when more precise calculations are necessary. For example, if lead credit is being pursued, these hour-by-hour tools are required to calculate the reduction in energy costs.
Let me summarize that, Mick. To recap, control the heat rejection equipment to maintain the entering condenser water temperature if the chiller has a centrifugal compressor or if it is a positive displacement compressor and cooling takes priority over heating. Only control the leaving condenser water temperature if heating is more important than cooling, and either you have a positive displacement compressor or a centrifugal compressor where the chilled water temperature is allowed to rise. When performing an analysis, make sure to select an hour-by-hour tool like Trace and input the effect of heat recovery temperatures on the chiller capacity and efficiency. Now, let's get into our question and answer portion of the broadcast. If we don't get to yours while we're on the air, our goal is to get the answers out within 4 weeks. Court, I think the first question is going to go to you, and here it is. Is the auxiliary condenser available in a vented double wall construction suitable for potable water service?
Good question. Trane builds the auxiliary condenser with just a standard shell and tube design, so a double wall construction isn't available from the factory. Depending upon what your local code requirements are, a secondary heat exchanger will be needed in the system.
Thanks, Court. Sure. Dave, this next one's for you. In a decoupled chiller plant with several heat recovery chillers, can more than one heat recovery chiller be placed on the load side of the bypass line?
The answer to that is yes, and that's the best place to put your heat recovery chillers. If you have more than one, they should all be there. And in fact, you might want to consider placing one of the cooling only chillers on the load side. That way it'll be the one that gets the diluted temperature.
Thanks, Dave. Mick, this one's for you. One of my clients would like to know, what about air-cooled? Is it possible to utilize a recovery heat exchanger in lieu of the condenser coil?
This broadcast was looking at waterside heat recovery. In the past, we've had some air-cooled chiller heat recovery products, and they weren't used very much. People have done it in the past, but we don't see it very much. It's probably a little bit harder on air-cooled chillers, and I guess that's where I'd take it at this point.
Okay, thanks, Mick. I think this one's for you also.
Cool.
The location of V2 conflicts with the recommendations of cooling tower and pump manufacturers. For example, varying the flow to the spray header and head by restricting flow on the pump suction.
Oh, yeah, we probably put the valve V2 in the wrong place on the diagrams. We'll look back at that and change both our diagrams. It should be not at the inlet to the pump, but at the outlet of the pump, and a valve in that portion. Thanks for pointing that out, whoever that was. We'll get that taken care of in the manual and in future presentations.
Thanks, Mick. Court, this is going to be our last question. This one's for you. At 115 degrees, the chiller couldn't unload very far. Would this have been different if the selection was at 105?
Another good question. The simple answer to that is yes. Basically, with any centrifugal chiller, the more you reduce the lift, the easier it is for the unit to unload. In fact, on the example that was shown, I initially selected the chiller at 105 degrees, but the unit actually unloaded so well, it wasn't really a good example to show in terms of how heat recovery units can run into unloading issues, so I changed it to 115 degrees.
Thanks, Court. Well, it's time to wrap up again. Mick, could you summarize the technical side of the broadcast for us, please?
You bet, Jeannie. Whether it's required by code, done to save operating costs, or to reduce a facility's environmental impact, waterside heat recovery makes sense for a significant number of applications. From a heat recovery temperature standpoint, if the purpose is to heat or preheat makeup water for service water heating and potable water, recovering heat at 85 to 95 degrees makes sense. If instead we're attempting to heat either outdoor or supply air streams, ASHRAE gives the guidance of water temperature of 105 to 110 degrees Fahrenheit. Now, some of the reasons are that the heat recovery water temperature adversely affects chiller capacity and efficiency, and the effect is dependent on the type of compressor that's involved. For positive displacement compressors, that is scrolls, recips, and screws, as the heat recovery temperature increases, both the capacity and efficiency decrease. We need to account for this in any analysis of the system. From a control perspective, positive displacement compressors can be controlled using either entering or leaving condenser water temperature. If the priority is cooling, control the heat rejection loop using the entering condenser water temperature. If heating is priority, then leaving condenser water temperature can be used. If centrifugal compressors are used to make higher water temperatures, the chiller can usually still make cooling capacity, but the efficiency decreases at both heat recovery and cooling only conditions. Also, the higher the temperature, the more likely that surge will occur at higher part loads. As for control, entering condenser water temperature control should be used for centrifugal compressor chillers. An exception being if the chiller is operating in the heating mode and chilled water temperature is allowed to rise. From a system standpoint, chiller location is critical. In the side stream position, it's easy to operate the chiller to provide heat as its priority, and since the chilled water temperature is elevated, the chiller efficiency increases. If it's piped in the preferential position on the load side of the bypass line, anytime the chiller is operating, it will allow the maximum amount of heat to be recovered. Here's some high-level system guidance as we wrap up today's broadcast. When considering waterside heat recovery, first, we need to make sure that we have heat to recover, which generally means simultaneous heating and cooling loads. As Dave showed, it may be beneficial to false load a chiller to provide heat recovery in some applications. Next, since higher heat recovery temperatures reduce chiller capacity and efficiency, select the lowest heating temperatures that meet the needs. Once the chiller is selected, determine which system configuration makes the most sense. Often, the side stream position provides the widest array of benefits. Finally, design and control the system properly. For centrifugal chillers, control the heat rejection loop to maintain a constant entering condenser water temperature. For positive displacement chillers, determine whether heating or cooling is a priority and control the system to provide that function. Jeannie, take us home.
Thanks, Mick. There are a number of publications available to get information on waterside heat recovery. Mick has recently published an Engineers Newsletter addressing this topic, and there's a Trane application manual that goes into a significant level of detail. A bibliography detailing these and additional resources is available from your local site coordinator. Past broadcasts are available on tape or DVD, depending on the vintage. Please check out the website for information on specific broadcasts. We thank you in advance for filling out the evaluation before you leave. Now we have 2 broadcasts remaining for this year. We will be back in September to cover various methods of humidity control. Some of them have been discussed in past broadcasts, but we'll go into more depth in the fall. And a topic that's been requested by quite a few viewers is information on U.S. Green Building Council's LEED program. Instead of covering the LEED requirements, which many of you are probably familiar with, our broadcast in November will highlight several LEED certified projects and how they achieved credit points within those sections that HVAC systems affect. Thanks for joining us today. We look forward to seeing you in September.